Pluto is perhaps the most famous of them, a dwarf planet about 2,377 kilometres in diameter, smaller than Earth's moon but large enough to have mountains, plains, and a thin atmosphere that freezes and thaws as it moves along its elongated orbit. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a landscape far more complex than anyone had expected. There were glaciers of nitrogen ice, towering mountains of water ice, and vast plains so smooth that they appeared geologically young. It was a reminder that even small worlds in the distant solar system can be dynamic and intriguing. But Pluto is only one of many objects in the Kuiper Belt. There are others: Eris, Haumea, Makemake, and many more, some nearly as large as Pluto, others much smaller. Astronomers estimate that there may be hundreds of thousands of objects larger than 100 kilometres across, and countless smaller ones. These objects are remnants, leftovers from the early solar system that never merged into larger planets. In a sense, the Kuiper Belt is a fossil record, preserving material from billions of years ago, material that has remained largely unchanged in the cold and darkness. The orbits of these objects are also different from those of the planets. While the planets follow relatively flat circular paths, many Kuiper Belt objects have elongated or tilted orbits, influenced by Neptune's gravity and by the complex history of planetary migration early in the solar system's history. That history is an important part of the story. Astronomers believe that the giant planets did not form exactly where they are today. In the early solar system, Jupiter, Saturn, Uranus, and Neptune may have migrated outward, scattering smaller objects as they moved. Some of those objects were ejected entirely, flung into interstellar space. Others were pushed into distant orbits, forming the Kuiper Belt and perhaps even the much more distant Oort Cloud. So the Kuiper Belt is not just a collection of icy bodies, it is evidence of the solar system's past, a record of the gravitational reshaping that took place long before Earth formed its oceans or life began to emerge. Another subtle but important change occurs as you move into the Kuiper Belt. The Sun's gravitational pull, while still dominant, is no longer overwhelmingly strong compared to other influences. Passing stars, the tidal forces of the Milky Way galaxy, and other subtle effects begin to matter more. This is what it means to say that the Sun begins to lose its grip. Not that its gravity disappears, but that its control becomes less absolute. Objects in the Kuiper Belt are still bound to the Sun, still orbiting it, but their orbits can be more easily perturbed, more easily altered over long periods of time. The solar system, in this sense, becomes less like a tightly bound system and more like a wide, diffuse region, with objects scattered across enormous distances. If you were travelling outward through the Kuiper Belt, the journey would feel very different from travelling among the planets. There would be no large worlds dominating the view, no bright rings or massive cloud tops, only occasional distant objects, faint and cold, drifting in the darkness. The silence would feel deeper, the emptiness more complete. And yet, the Kuiper Belt is still part of the solar system, still within the Sun's domain. Spacecraft like New Horizons continue to explore this region, sending back data from objects billions of kilometres away. Signals from New Horizons take more than 6 hours to reach Earth, a reminder of just how far it has travelled. There is something quietly astonishing about that. A small machine, built on Earth, moving through a region so distant that sunlight itself has grown faint, still able to communicate across billions of kilometres of empty space. That connection, that thin thread of radio waves linking Earth to a spacecraft at the edge of the planetary system, is one of the ways we measure and understand the scale of the solar system. Long before spacecraft ever reached the distant frontier beyond Neptune, Pluto was little more than a faint point of light in a telescope, moving slowly against the background of stars. When it was discovered in 1930, astronomers believed they had found the 9th planet, a lonely world marking the outer edge of the solar system. For decades, Pluto held that role in textbooks and in people's imaginations, the last known stop before the darkness between the stars. At the time, the solar system felt smaller in a conceptual sense. 8 planets near the Sun, and then Pluto, far away but still part of a neat sequence. The idea of a boundary was comforting, as if the solar system was something contained and well-defined. But as telescopes improved and surveys of the outer regions became more thorough, astronomers began to notice that Pluto was not alone. other objects, faint and distant, were being discovered in similar orbits, sometimes nearly as large as Pluto itself. The picture began to change. Pluto was not the outermost planet after all. It was one member of a much larger population. Understanding this shift requires thinking again about scale. Pluto's average distance from the Sun is about 39 astronomical units, but its orbit is highly elliptical, carrying it as close as about 30 astronomical units, and as far as nearly 50. That means there are times when Pluto actually comes closer to the Sun than Neptune does, though the two never approach each other closely because their orbits are tilted in different planes. This elongated orbit is one of the clues that Pluto is different from the classical planets. The planets follow relatively flat, nearly circular paths around the Sun. Pluto's orbit is tilted and stretched, more like those of many Kuiper Belt objects than like those of the major planets. And that similarity turned out to be important. As astronomers continued to search the outer solar system, they discovered other worlds of comparable size. One of the most significant was Eris, found in 2005, slightly more massive than Pluto and orbiting even farther from the Sun. The discovery of Eris forced scientists to confront a difficult question. If Pluto was a planet, should Eris also be considered one? And if so, how many more planets might there be waiting to be found? Rather than expanding the list indefinitely, astronomers chose to refine the definition of a planet. In 2006, the International Astronomical Union introduced the category of dwarf planets, and Pluto was reclassified accordingly. It remained an important world, but it was no longer considered one of the major planets. For many people, this change felt surprising, even disappointing. Pluto had been part of the familiar picture of the solar system for generations, but scientifically the reclassification reflected a deeper understanding. Pluto was not an isolated outer planet. It was part of a vast population of distant objects, the Kuiper Belt, a region that extends far beyond Neptune. Thinking about Pluto today means thinking about that broader context. It is one of many worlds at the edge of the familiar, a region where distances are so great and sunlight so faint that the solar system begins to feel less like a collection of planets and more like a wide, scattered frontier. When the New Horizons spacecraft approached Pluto in 2015, it transformed our understanding of this distant world. Before the flyby, Pluto was little more than a blurry disk in the best telescopes. Afterward, it became a landscape, a place with mountains, plains, and an atmosphere. One of the most striking features discovered was a vast heart-shaped region known as Sputnik Planitia, a basin filled with nitrogen ice that appears to be slowly flowing, reshaping the surface over time. The presence of such active geology was unexpected. At such low temperatures, far from the Sun, many scientists had assumed Pluto would be geologically dead, frozen and unchanging. Instead, it turned out to be a dynamic world, reminding us that distance from the Sun does not necessarily mean inactivity. Mountains of water ice rise several kilometres above the plains, their surfaces rugged and sharp. The atmosphere, though extremely thin, changes with the seasons, freezing onto the surface when Pluto moves farther from the Sun and sublimating back into gas when it comes closer. These discoveries revealed something important about the outer solar system. Even small worlds, even those billions of kilometres away, can be complex and evolving places. But Pluto is only one of many such worlds. Eris, as mentioned earlier, orbits at an average distance of about 68 astronomical units, much farther than Pluto. Its surface is thought to be coated with frozen methane and nitrogen, reflecting sunlight so efficiently that it appears bright despite its enormous distance. Haumea, another dwarf planet, is unusual in a different way. It rotates so rapidly that it has been stretched into an elongated shape, more like a flattened ellipsoid than a sphere. It is also surrounded by a family of smaller objects, fragments thought to have formed from a collision long ago. Makemake, yet another dwarf planet, lies in a distant orbit and has a surface rich in methane ice, giving it a reddish appearance in telescopic images. And beyond these named worlds are countless smaller objects, many still unnamed, many still undiscovered, drifting in the cold darkness beyond Neptune. The distances between these objects are immense. Even though they belong to the same general region, the Kuiper Belt, they are separated by millions or even hundreds of millions of kilometres, a spacecraft travelling between them would spend years crossing empty space, with nothing visible but distant points of light. That emptiness is part of what defines this region. It is not a crowded field of debris, but a vast expanse where objects are scattered thinly across enormous distances. The Sun, seen from Pluto, appears about 1,000 times fainter than it does from Earth. It still shines, still casts shadows, but the light is pale and distant, more like a brilliant star than the blazing disk we see in our sky. Temperatures there are extremely low, often below -220 degrees Celsius. Ices that would vaporize instantly on Earth remain solid, forming landscapes of frozen nitrogen, methane, and carbon monoxide. And yet, even at such distances, the Sun's gravity still holds these worlds in orbit. They remain part of the solar system, bound to the same star that warms Earth and drives the weather of our planet. That realization can be difficult to absorb. The solar system extends not just to the orbit of Neptune, not just to Pluto, but far beyond, into regions where objects take centuries or even millennia to complete a single orbit around the Sun. Pluto itself takes about 248 Earth years to circle the Sun once. That means it has not yet completed a full orbit since its discovery in 1930. It is still moving along the same long path, slowly tracing its course through the outer solar system. There is something quietly humbling about that timescale. Civilizations rise and fall on Earth while Pluto moves only a small fraction of its orbit. The dwarf planets of the Kuiper Belt mark a kind of threshold, the edge of what feels familiar. Beyond them, objects become smaller, more distant and harder to detect. The solar system continues, but it becomes increasingly diffuse, increasingly difficult to map. And yet, even here, we are still not near the true boundary of the Sun's influence. If you continue travelling outward past Pluto and the scattered dwarf worlds, something subtle begins to change. The solar system no longer feels defined by planets, or even by icy bodies drifting in distant orbits. Instead, the environment itself begins to shift. The space around you is still mostly empty, still dark, still cold, but it is no longer shaped only by gravity and distant sunlight. There is another influence at work, one that extends far beyond the orbits of the planets, far beyond the Kuiper Belt, reaching into a region where the Sun's presence is no longer visible in any familiar way. That influence is the solar wind. The Sun is not just a glowing sphere of light and heat. It is also constantly releasing a stream of charged particles, mostly electrons and protons, flowing outward in all directions at speeds of hundreds of kilometers per second. This outflow is called the solar wind, and although it is extremely thin, far more rarefied than any vacuum we can create on Earth, it fills the entire solar system. Near Earth, the solar wind is almost imperceptible. Our planet's magnetic field deflects most of these particles, creating the protective bubble known as the magnetosphere. Occasionally, some of the particles follow magnetic field lines into the upper atmosphere, producing the auroras, those shimmering curtains of green and red light that ripple across polar skies. But the solar wind does not stop at Earth. It continues outward, past Mars, past Jupiter, past Saturn and Neptune, expanding in all directions like an invisible tide moving through space. Eventually, however, it encounters something else: the thin gas and magnetic fields that exist between the stars. Interstellar space is not completely empty. It contains traces of hydrogen atoms, stray ions, and the faint influence of the galaxy's magnetic field. When the solar wind pushes against this interstellar medium, it begins to slow down, compress, and change. The region carved out by the solar wind, this enormous bubble surrounding the Sun, is called the Heliosphere. Understanding the Heliosphere is essential if we want to understand how big the solar system really is, because in one sense, this bubble marks the farthest reach of the Sun's direct physical influence. Beyond it, space is no longer dominated by particles from our star, but by the environment of the galaxy itself. The Heliosphere is vast beyond ordinary imagination. Its boundary lies roughly 120 astronomical units from the Sun in the direction that spacecraft have measured, though its shape is not perfectly spherical. Because the solar system is moving through interstellar space, the Heliosphere is slightly compressed in the direction of motion and stretched out behind, rather like the wake trailing behind a boat moving through water. If you were travelling outward, You would not encounter this boundary as a sharp wall. Instead, the transition would be gradual. First, you would cross a region called the Termination shock. Here, the solar wind slows from supersonic speeds to subsonic speeds as it begins to feel the pressure of the interstellar medium. The change is not dramatic to the eye, because there is little to see, but instruments would detect a shift in particle energies and magnetic fields. Farther out lies the Heliosheath, a vast, turbulent region where the slowed solar wind piles up, swirling and mixing as it presses outward against interstellar space. This region is enormous, tens of astronomical units thick, a kind of borderland where the sun's influence fades gradually rather than abruptly. And then at last comes the heliopause, the outer boundary of the heliosphere. This is the point where the pressure of the solar wind balances with the pressure of interstellar space. Beyond this boundary, the particles surrounding you no longer originate primarily from the sun. Crossing the heliopause means entering interstellar space. It may sound like a dramatic moment, but in reality, it is quiet and subtle. There is no flash of light, no sudden darkness, no visible line marking the transition. Only instruments can detect the change. A drop in solar particles, a rise in cosmic rays from distant stars, a shift in magnetic fields. And yet, scientifically, it is one of the most significant boundaries in our cosmic neighbourhood. For decades, the heliosphere was only a theoretical concept, something predicted by models but not directly observed at its edge. Then, in the early 21st century, humanity achieved something extraordinary. The Voyager spacecraft, launched in 1977, travelling faster and farther than any human-made objects before them, began to approach this distant frontier. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018. These spacecraft are now in interstellar space, still sending back faint signals, still carrying instruments that measure the environment far beyond the planets. It is remarkable to think about those signals. Radio waves travelling billions of kilometres, taking more than 20 hours to reach Earth, carrying information from regions of space no human has ever seen directly. The Voyagers are still moving outward, slowly but steadily, each second carrying them farther from the sun, deeper into the galaxy. Long after their instruments fall silent, they will continue drifting, silent messengers from a distant star system. Thinking about the heliosphere also helps us understand something about the sun itself. Stars are not isolated objects. Each one interacts with its surroundings, shaping the space around it with winds, radiation, and magnetic fields. Our heliosphere is just one example of this process, a bubble carved into the interstellar medium by the steady flow of particles from our star. Other stars likely have their own astrospheres, similar bubbles of influence surrounding them, though we cannot observe most of them directly. In that sense, the heliosphere is both unique and universal, a feature of our solar system that reflects a broader pattern throughout the galaxy. There is also something quietly reassuring about the heliosphere, because it serves as a kind of shield. The solar wind helps deflect some of the high-energy cosmic rays that travel through interstellar space, reducing the amount of radiation that reaches the inner solar system. Without this protective bubble, conditions near Earth might be very different, perhaps less hospitable to life. The heliosphere, then, is not just a boundary, it is part of what makes our environment what it is. And yet, even this enormous bubble is not the outermost extent of the solar system in every sense. Gravity reaches farther than the solar wind. The sun's gravitational influence extends far beyond the heliopause, holding distant icy bodies in orbits that may take millions of years to complete. This is an important distinction. The heliosphere marks the boundary of the sun's particle influence, but not necessarily the boundary of its gravitational domain. If you imagine the solar system as a kind of territory, the heliosphere is like the edge of the atmosphere, where the air thins and the sky turns black. But gravity continues to act beyond that point, binding distant objects in slow, distant orbits. And that brings us to a question that astronomers still explore. How far does the sun's gravity really extend? Where is the true outer edge of the solar system, if such a thing can be defined at all? The answer may lie in a region so distant that no spacecraft has ever reached it, a vast cloud of icy bodies that surrounds the solar system at distances tens of thousands of times greater than Earth's orbit. But before we turn to that distant frontier, It is worth lingering for a moment on the idea of the heliosphere itself, because it changes how we think about size in a subtle way. Until now, much of our discussion has focused on objects, planets, moons, asteroids, dwarf planets. These are tangible things, places with surfaces and orbits, worlds that can be mapped and photographed. The heliosphere is different. It is not a solid object, not even a collection of objects, but a region defined by motion and energy, by streams of particles moving through space. It is invisible to the eye, yet enormous in scale, far larger than the region occupied by the planets. This reminds us that the solar system is not just a collection of worlds. It is also an environment shaped by forces and fields that extend far beyond anything we can see directly. If you were drifting somewhere near the heliopause, far beyond Pluto, the Sun would appear as an extremely bright star, far brighter than any other, but still just a point of light. The nearest planets would be impossibly distant, lost in the glare near the Sun. The sky would be filled with stars, sharp and steady, unblinking in the darkness. And around you, though invisible, would be the boundary between two different cosmic environments, the realm shaped by our star and the vast interstellar medium beyond. That realization carries a certain quiet weight. It reminds us that the solar system is not an isolated island, but a region embedded within a much larger galaxy, moving through space surrounded by other stars, other systems, other bubbles carved by distant suns. Long before anyone expected a human-made object to travel beyond the planets, 2 small spacecraft were launched from Earth with a very specific purpose. They were not originally intended to leave the solar system at all. Their mission was to take advantage of a rare planetary alignment, a configuration that happens only about once every 176 years, in which the giant planets line up in a way that allows a spacecraft to visit several of them in sequence, using each planet's gravity to gain speed and redirect its path. These spacecraft were Voyager 1 and Voyager 2, launched in 1977, only weeks apart. At the time, their planned journeys were ambitious enough: fly past Jupiter and Saturn, study their moons and rings, and send back images and data that would transform our understanding of the outer planets. No one could be entirely sure what would happen after that. The spacecraft would keep moving, of course, but how far they might go and what they might encounter was still uncertain. To appreciate what Voyager accomplished, it helps to imagine the scale of the journey from the beginning. When Voyager 1 lifted off from Earth, it began as all spacecraft do, climbing through the atmosphere, circling the planet, and then accelerating outward. In those early hours, it was still close to home, still within the region dominated by Earth's gravity. Soon after, it escaped Earth's pull and entered orbit around the Sun, beginning the long arc outward toward Jupiter. The trip to Jupiter alone took nearly 2 years. That distance, which now feels modest compared to where Voyager is today, was at the time an enormous step outward, farther than any spacecraft had travelled before, while still remaining operational and under close observation. When Voyager 1 arrived at Jupiter in 1979, it revealed a world more dynamic than anyone had expected. Active volcanoes were discovered on the moon Io, erupting continuously, driven by the immense tidal forces exerted by Jupiter's gravity. Europa's smooth, icy surface hinted at a hidden ocean beneath. The intricate structure of Jupiter's rings and the complexity of its atmosphere became clearer than ever before. After its encounter with Jupiter, Voyager 1 used the planet's gravity to change its trajectory, accelerating and heading towards Saturn. This technique, called a gravity assist, works by borrowing a tiny amount of a planet's orbital energy. The spacecraft falls toward the planet, swings around it, and departs at a higher speed, redirected along a new path. Saturn was reached in 1980. There, Voyager revealed extraordinary details about the rings, showing them to be far more complex and structured than previously imagined. The moon Titan, shrouded in a thick atmosphere, drew particular interest. Because Titan was such an intriguing target, Voyager 1's trajectory was adjusted to pass close to it, and that decision had a consequence. After Saturn, Voyager 1 would no longer be aligned to visit Uranus or Neptune. Instead, it was flung upward, out of the plane of the planets, beginning a journey that would eventually carry it toward interstellar space. Voyager 2 followed a different path. After Jupiter and Saturn, it continued onward to Uranus, arriving in 1986 and then to Neptune in 1989, becoming the only spacecraft ever to visit those distant worlds. With that final planetary encounter, Voyager 2, like its twin, was set on a course that would carry it beyond the known planetary region of the solar system. From that point forward, the Voyagers were no longer explorers of planets. They became explorers of distance itself. Both spacecraft continued outward, moving through regions of space where the sun's warmth is faint, where the planets are far behind, and where the environment is shaped less by visible objects and more by invisible forces. Their instruments, designed to measure magnetic fields, charged particles, and cosmic rays, began to study the outer reaches of the Heliosphere. It is difficult to grasp just how far they have travelled. Voyager 1 is now more than 160 astronomical units from the Sun. That means it is more than 160 times farther from the Sun than Earth is. Light, travelling at nearly 300,000 kilometres per second, takes over 20 hours to make the round trip between Earth and Voyager 1. Imagine sending a message and waiting nearly a full day to hear the reply. That delay is part of the daily reality of communicating with spacecraft at such distances. Another remarkable aspect of the Voyagers is their longevity. Designed for missions expected to last only a few years, they have continued operating for decades, powered by radioisotope thermoelectric generators that convert heat from the decay of plutonium into electricity. Over time, their power output has slowly declined, and engineers have had to shut down some instruments to conserve energy, but the spacecraft continue to function, still sending back data from regions no human-made object had ever reached before. In 2012, Voyager 1 crossed the heliopause, becoming the first spacecraft to enter interstellar space. Voyager 2 followed in 2018. These crossings were not marked by dramatic visual changes, but by subtle shifts in the data. A drop in particles from the solar wind, an increase in cosmic rays from beyond the solar system, and changes in the magnetic field. For the first time, humanity had instruments operating in the space between the stars. There is something quietly profound about that fact. The Voyagers carry no crew, no ability to return, no means of repair. They move steadily outward, year after year, following trajectories set in motion decades ago, each second carrying them farther from the Sun. And yet, despite their distance, they remain connected to Earth by a faint stream of radio signals, detected by enormous antennas of the Deep Space Network. These antennas must be precisely aimed, because the signals arriving from Voyager are incredibly weak, comparable to the power of a small household appliance spread across billions of kilometres. That connection, fragile as it is, links our world to the farthest reaches of the solar system. The Voyagers also carry something symbolic, a message intended not for us, but for whoever or whatever might one day encounter them. Each spacecraft contains a golden record, a phonograph disc plated in gold, along with a stylus and instructions for playback. The record contains sounds and images from Earth, greetings in many languages, music from different cultures, the sounds of wind and rain, of footsteps and laughter. It also contains a map showing the position of the Sun relative to nearby pulsars, a kind of cosmic address, in case anyone should ever find the spacecraft and wonder where they came from. The chances of that happening are extremely small. Space is vast beyond imagination, and the Voyagers are tiny objects moving through it, but the records were included as a gesture, a quiet statement that humanity, having reached beyond its own world, chose to carry with it a trace of who we are. Thinking about the Voyagers changes how you think about the size of the solar system. Before them, the outer regions were largely theoretical, understood through observation and calculation but not through direct measurement. The Voyagers turned those distant regions into places we have visited, places from which we have received data. And yet, even after travelling for nearly half a century, the Voyagers have not reached the true outer limits of the Sun's gravitational influence. They're only beginning to pass through the outermost regions of the Heliosphere and into interstellar space, still far from the distant Oort Cloud, which may extend tens of thousands of astronomical units from the Sun. At their current speed, it would take Voyager tens of thousands of years to reach the inner edge of that distant cloud, and far longer to pass through it entirely. That perspective is humbling. The spacecraft that represent the farthest reach of human exploration have only begun to leave the solar system in the broadest sense. the true outer regions remain unimaginably distant. Another way to understand the scale is to think about time. Voyager 1 travels at about 17 kilometers per second relative to the Sun. That is incredibly fast by human standards. A jet aircraft moves at less than 1/10 of that speed. A rifle bullet travels at less than 1/20th. And yet, even at that speed, crossing the solar system takes decades. Distance in space is so vast that even our fastest machines require lifetimes to traverse it. There is also something quietly moving about the fact that the Voyagers are now the most distant human artifact ever created. Every human being who has ever lived remains far behind them, on a small planet orbiting a distant star. The spacecraft carry with them traces of our knowledge, our curiosity and our desire to explore. Long after their instruments fall silent, after their power is exhausted and their transmitters go quiet, the Voyagers will continue drifting. They will orbit the centre of the Milky Way along with the Sun, taking hundreds of millions of years to complete a single galactic orbit. In that sense, they have already begun journeys far longer than any human civilization has yet endured. Imagining their path can be strangely calming. Two small objects moving steadily through darkness, guided only by the laws of physics, carrying with them a silent record of a distant world. There is no urgency in their motion, no deadlines, no schedules, only steady movement second by second, year after year, and their journey helps answer a deeper question about the size of the solar system, because it shows that the boundary of our cosmic neighbourhood is not a simple line, not a place you reach in a day or even a decade, but a vast and gradual transition extending far beyond the planets. The Voyagers remind us that the solar system is not just the region of planets we learned about in school. It is a much larger environment, one that stretches outward for distances so great that even our farthest spacecraft are only beginning to explore it. Far beyond the path of Neptune, beyond the scattered dwarf planets, and even beyond the invisible boundary of the Heliosphere, there is a region that stretches the imagination almost to its limit. Unlike the planets, or even the Kuiper Belt, this region has never been directly observed. No spacecraft has reached it, no telescope has imaged it clearly, and yet astronomers are almost certain it exists. This distant region is known as the Oort Cloud. To understand why scientists believe in something so remote, it helps to think about comets. For centuries, comets were mysterious visitors, appearing suddenly in the sky with long, glowing tails, then fading and disappearing again. Some returned regularly, like Halley's Comet, which comes back roughly every 76 years. Others appeared only once, following paths that carried them far out of the solar system, perhaps never to return. When astronomers began calculating the orbits of these long-period comets, they noticed something remarkable. Many of them seemed to arrive from extremely distant regions, approaching the Sun from all directions, not just from the flat plane where the planets orbit. Their trajectories suggested a source not in a disk like the Kuiper Belt, but in a vast, roughly spherical distribution surrounding the solar system. In 1950, the Dutch astronomer Jan Oort proposed an explanation. He suggested that the solar system is surrounded by a distant cloud of icy bodies, remnants from the formation of the planets, orbiting at distances tens of thousands of astronomical units from the Sun. Occasionally, passing stars or gravitational disturbances would nudge some of these objects inward, sending them toward the Sun as long-period comets. This idea fit the observations remarkably well, and over time it became widely accepted, even though the Oort cloud itself remains too distant and too faint to observe directly. The scale of the Oort cloud is difficult to grasp. While the Kuiper Belt extends to perhaps 50 astronomical units, the inner edge of the Oort cloud may begin thousands of astronomical units from the Sun, and the outer edge could lie as far as 50,000 to 100,000 astronomical units away. To put that into perspective, 1 astronomical unit is the distance from Earth to the Sun. At 100,000 astronomical units, you're nearly halfway to the nearest stars. Light, which takes only 8 minutes to travel from the Sun to Earth, would take more than a year to cross the diameter of the inner Oort cloud and many years to cross its outer reaches. At such distances, the Sun would no longer appear as a bright disk or even a brilliant star. It would be just another point of light in the sky, brighter than most stars but not overwhelmingly so. And yet, even there, its gravity still holds sway. binding these distant icy bodies in slow, elongated orbits that may take millions of years to complete. Imagining the Oort Cloud requires a different way of thinking about the solar system. Up to this point, we have been picturing a relatively flat system, a disk of planets orbiting in roughly the same plane. The Oort Cloud, by contrast, is thought to be spherical, surrounding the solar system in all directions like a vast halo. If the planetary region were the size of a coin, the Oort Cloud would extend out to the size of a city. Within that enormous volume, the objects themselves are tiny and widely separated. There may be trillions of icy bodies in the Oort Cloud, but the distances between them are so great that a spacecraft travelling through it might pass for years without encountering anything larger than a speck of ice. It would feel less like flying through a cloud and more like drifting through a vast, dark ocean with occasional distant grains of dust. Temperatures in the Oort Cloud are extremely low, only a few degrees above absolute zero. Sunlight is faint, barely distinguishable from the glow of distant stars. The environment is quiet beyond any human experience, with no nearby planets, no significant radiation from the sun, and only the slow drift of distant icy bodies moving along their immense orbits. And yet, this region is still part of the solar system. That is one of the most surprising aspects of the Oort Cloud. The solar system is not just the region of planets, or even the region of the Heliosphere. It may extend tens of thousands of times farther than the distance from Earth to the Sun, forming a gravitational domain that reaches deep into interstellar space. The boundary between the solar system and the galaxy is not a sharp line. It is a gradual transition, where the Sun's gravitational influence weakens until the gravitational pull of other stars and the tides of the Milky Way begin to dominate. At the outer edge of the Oort Cloud, an object might be only loosely bound to the Sun, easily perturbed by passing stars or molecular clouds drifting through the galaxy. Over millions of years, some of these objects may be stripped away entirely, becoming free-floating bodies wandering the interstellar medium. Others may be nudged inward, beginning long journeys that eventually bring them into the inner solar system as comets, glowing briefly in the sunlight before retreating once more into the darkness. That slow exchange of material between the solar system and the galaxy is part of what makes the Oort Cloud so fascinating. It is not just a boundary, but a dynamic region, shaped by the gravitational influence of nearby stars, by the motion of the Sun through the Milky Way, and by events that unfold over timescales far longer than human history. Thinking about those timescales can be strangely calming. An object in the outer Oort Cloud might take millions of years to complete a single orbit around the Sun. Entire ice ages on Earth would pass while that distant body moved only a small fraction of its path. Civilizations would rise and fall, continents would shift, species would evolve, and still, the distant comet would continue its slow journey through the darkness. The Oort Cloud also reminds us that the solar system is not isolated. The Sun is one of hundreds of billions of stars in the Milky Way, and as it orbits the galactic centre, it passes through regions of varying density, sometimes closer to other stars, sometimes farther away. Over billions of years, these encounters have likely shaped the structure of the Oort Cloud, stirring it, reshaping it, perhaps even capturing or losing objects along the way. In that sense, the outermost solar system is not a fixed, unchanging structure, but part of a larger galactic environment, influenced by forces far beyond the reach of any spacecraft. And yet, despite its distance and mystery, the Oort Cloud plays a role in our own experience of the night sky. Many of the bright comets that have fascinated observers throughout history, comets that appeared suddenly and dramatically, may have originated in this distant reservoir. When we see a comet blazing in the sky, with its glowing tail stretching across the stars, we may be witnessing an object that has spent most of its existence tens of thousands of astronomical units from the Sun, travelling for millions of years before making a brief visit to the inner solar system. There is something quietly extraordinary about that thought, that a fragment of ice formed in the earliest days of the solar system can journey across such immense distances and become visible to human eyes, if only for a short time. The Oort Cloud, then, represents a kind of frontier, not a sharp edge, but a vast and diffuse boundary where the solar system gradually fades into the wider galaxy. It is likely that no spacecraft will reach it for many centuries, perhaps millennia given current technology. The distances are simply too great. Even Voyager, moving faster than any other human-made object, would take tens of thousands of years to reach the inner edge of the Oort Cloud and far longer to cross it entirely. And yet, knowing that this distant region exists changes how we think about the size of our cosmic neighbourhood. The solar system is not a small collection of planets orbiting a star. It is a vast domain, stretching far beyond the limits of direct observation, extending into regions so distant that the Sun itself becomes just another star in the sky. At this point, after travelling outward in our minds from Earth to the Moon, past the planets, through the Kuiper Belt, and all the way to the distant reaches of the Heliosphere and the imagined boundary of the Oort Cloud, the numbers involved have grown so large that they begin to lose their meaning. Tens of millions of kilometres, billions of kilometres, tens of thousands of astronomical units. These figures are precise, but precision alone does not always help us feel the scale of something, so it can be helpful to do something different for a moment. Instead of trying to stretch our minds to match the solar system, we can shrink the solar system down to match our minds. We can imagine it as a map, or a model, or a landscape small enough to walk through, something that translates cosmic distances into steps, meters, and familiar spaces. This approach doesn't change the proportions. The planets remain just as small compared to the distances between them. But when everything is scaled down together, the relationships become easier to grasp, and the vastness begins to feel more real. Let's start with a simple example. Imagine placing the Sun on a large open field and shrinking it to the size of a basketball. A basketball is about 24 centimetres across, easy to picture, easy to hold. Now imagine that everything else in the solar system shrinks by the same proportion. At that scale, Earth would be about the size of a small pea, roughly 2 millimetres across, and the distance between the basketball Sun and that tiny pea Earth would not be a few steps. It would be about 26 metres, roughly the length of a modest swimming pool. Already that feels different from the diagrams we usually see. The Sun and Earth are not close together at all. There is a wide stretch of empty space between them, space you would have to walk across to reach the tiny speck that represents our world. Now imagine continuing outward. Mars, even smaller than Earth in this model, would lie about 40 metres from the basketball Sun. Jupiter, which in reality is enormous compared to Earth, would still only be about the size of a grape, but it would sit more than 130 metres away. Saturn, slightly smaller, would be around 240 metres out, nearly a quarter of a kilometre from the centre. Uranus and Neptune would lie even farther, several hundred metres away, tiny spheres in the distance, barely noticeable unless you knew exactly where to look. And Pluto, if included in this model, would be nearly a kilometre away from the Sun, smaller than a grain of sand. What becomes striking when you imagine this is not just how small the planets are, but how far apart they are. Walking from the basketball Sun to Neptune would take several minutes, and most of that walk would be spent crossing empty space, seeing nothing but distant markers on the horizon. That emptiness is not an exaggeration. It is one of the defining features of the solar system. Another way to think about scale is to imagine compressing the solar system into something the size of a city. Suppose the Sun were placed at the centre of a large urban park. Mercury might be a tiny bead only a few dozen metres away. Earth would be a small dot a few hundred metres out. Jupiter might lie several kilometres from the centre, and Neptune perhaps 10 kilometres or more. At that scale, the Kuiper Belt would stretch beyond the edges of the city, and the Oort Cloud would extend far beyond, perhaps as far as neighbouring towns, or even across an entire region. In that version of the solar system, most of the space between worlds would feel like long stretches of highway, farmland, or open countryside. The planets themselves would be tiny landmarks scattered across enormous distances. These kinds of models help reveal something important. When we look at textbook diagrams, the planets often appear crowded together because the page cannot accommodate the true distances. If drawn accurately, the planets would be so far apart that the page would be mostly blank. The solar system, in reality, is mostly blank. There are also real-world models built at this kind of scale. In several places around the world, educators have created walking-scale solar system trails, where each step corresponds to millions of kilometres. Visitors begin at a large representation of the Sun, then walk for some distance before reaching Mercury, then farther to Venus, then farther still to Earth. What people often notice is how quickly the distances grow. The first few planets appear relatively close together, but as the walk continues, the gaps become larger and larger. By the time they reach Jupiter or Saturn, the earlier planets feel clustered near the starting point, and the outer markers are spread widely across the landscape. And if the model includes Pluto or the Kuiper Belt, those markers may be placed far beyond the others, sometimes at the edge of the trail or even beyond it, emphasizing just how large the solar system really is. There is something quietly effective about walking such a model. Each step takes time. Each stretch of empty ground becomes part of the experience. You begin to feel, rather than just calculate, the vastness involved. Another useful way to shrink the solar system into something relatable is to think in terms of travel times, but scale to human speeds. Imagine you could walk at a steady pace of 5 kilometers per hour through our basketball-sized solar system. Walking from the Sun to Earth, about 26 meters in this model, would take only a few seconds. But walking out to Jupiter, more than 130 meters away, would take nearly half a minute. Walking to Neptune, several hundred meters distant, would take a few minutes. That may not sound dramatic, but remember that the planets themselves are tiny. Most of the time would be spent crossing empty ground with nothing to see but distant markers. Now imagine extending this model to include the inner edge of the Oort Cloud. At the same scale, that boundary might lie tens of kilometers away, far beyond walking distance in a casual stroll, more like a long journey across a region than a walk in a park. And the outer edge might be hundreds of kilometers away, farther than many people travel in a day. This comparison helps show just how large the solar system truly is. The planetary region, from Mercury to Neptune, occupies only a small inner portion of the Sun's domain. Beyond it lies a vast frontier that stretches far into interstellar space. There is also something interesting about how shrinking the solar system changes our sense of the planets themselves. Jupiter, which feels enormous in astronomical discussions, becomes a grape in the basketball model. Earth becomes a tiny speck. The Sun, though still large compared to the planets, becomes something you could hold in your hands. That shift in perspective can be strangely grounding. It reminds us that size is always relative. The Sun is enormous compared to Earth, but small compared to many stars. Earth is large compared to a person, but tiny compared to Jupiter. And all of them together are small compared to the vastness of the solar system. Another approach is to imagine the solar system scaled to time rather than distance. Suppose the distance from the Sun to Neptune were represented by a single day's walk from sunrise to sunset. Earth would lie only a short time after dawn, Jupiter perhaps around midday, and Neptune near evening. The Oort Cloud would extend far into the night, long after the sun had set. In that sense, most of the solar system exists in the darkness beyond the familiar daylight of the planets. This kind of thinking also helps explain why exploration takes so long. Spacecraft, even moving at extraordinary speeds, still require years to cross the distances between planets. Voyager has been travelling for nearly half a century and is still within the broader gravitational domain of the Sun. If the solar system were a map you could unfold on a table, the planets would be tiny dots separated by vast blank areas. Most of the map would be empty, not because nothing exists there, but because space itself is so immense, and that emptiness is not just a curiosity. It has real consequences. It shapes how spacecraft travel, how signals are transmitted, how gravity acts, and how rare collisions between objects are. It also shapes our understanding of how planetary systems form, because the distances between bodies influence how they interact over billions of years. There is another quiet realization that comes from imagining the solar system as a map. Our entire human history, every city, every ocean crossing, every journey ever made, has taken place on a speck no larger than a grain of sand in that model. All of our concerns, ambitions and stories exist within a tiny fraction of the solar system's extent. And yet, from that small beginning, we have sent machines across billions of kilometers, measured distances to distant stars, and begun to understand the structure of our cosmic neighborhood. That ability to comprehend something so vast, even imperfectly, is one of the remarkable achievements of human curiosity. Once you begin to think about the solar system as a map, with planets reduced to tiny markers and distances stretched across fields or cities, one idea begins to stand out more than any other. It is not the size of the planets that defines the solar system, it is the emptiness between them. That emptiness is easy to overlook at first. When we see images of space in books or films, the scenes are often filled with glowing clouds, bright stars, or clusters of asteroids drifting close together. These images can be beautiful, but they give a misleading impression. Most of the solar system does not look like that at all. Most of it is quiet, dark, and nearly empty, with distances so large that even the nearest objects are separated by vast stretches of nothing. To understand this properly, it helps to think again about the scaled models we imagined earlier. In the basketball-sized solar system, the planets were tiny and widely spaced, and most of the journey between them was spent crossing open ground. Now imagine that same model at night, in a wide field, with only a few faint markers visible in the distance. That is closer to what space really feels like. Even in the asteroid belt, which many people picture as crowded, the distances between large objects are enormous. A spacecraft can travel through that region without encountering any nearby rocks at all, unless it deliberately aims for one. The asteroids are scattered across millions of kilometres, each following its own orbit, rarely coming close to another. The same is true in the Kuiper Belt, and even more so in the regions beyond. Objects are separated by such immense distances that collisions are rare on human timescales. Most of the time, space is simply empty. But what does empty actually mean? It does not mean absolute nothingness. Even in the emptiest regions of interplanetary space, there are still particles, atoms of hydrogen, stray dust grains, and streams of charged particles from the solar wind. But these are incredibly sparse. Near Earth's orbit, there may be only a few particles per cubic centimetre, far fewer than in any vacuum we can produce in a laboratory. Farther from the Sun, the density drops even more. In the outer solar system, space becomes so thin that the particles are separated by distances measured in centimetres or metres. It is an emptiness beyond ordinary experience, quieter and more complete than anything we encounter on Earth. Sound cannot travel there, because there is no air or water to carry vibrations. A spacecraft moving through space does so in complete silence, hearing only the faint hum of its own systems. There is also very little resistance. On Earth, moving objects are constantly slowed by friction with the air or ground. In space, once a spacecraft is set in motion, it continues moving unless acted upon by gravity or by firing its engines. This is why spacecraft can coast for years, drifting along trajectories determined long ago. That quiet, frictionless motion is one of the defining characteristics of space. It is a place where motion persists, where objects follow their paths without interruption, where the laws of physics unfold in their simplest form. Another way to grasp the emptiness is to think about visibility. If you were floating in interplanetary space, far from any planet, the sky would not look crowded or dramatic. The sun would shine as a bright disk, and the stars would appear sharp and steady, but most of the time, you would see nothing else. Even large planets are difficult to see from a distance. Jupiter, enormous as it is, would appear as a bright point until you were relatively close. The smaller planets would be invisible to the naked eye at most distances. This means that a traveller moving between worlds would spend most of the journey with no visible destination, navigating by instruments and calculations rather than by sight. The destination would remain a faint point of light until the final stages of the approach. That experience has been described by astronauts and mission planners alike. Space travel is not a constant parade of scenery. It is long periods of quiet motion punctuated by brief moments of arrival. The emptiness also affects temperature in ways that may seem surprising. Space is often described as cold, and in many ways it is, but not because it is filled with cold air. Instead, objects in space lose heat slowly by radiation, and they gain heat only from sunlight or internal sources. A spacecraft in sunlight can become quite warm, while one in shadow can become extremely cold. The temperature depends on exposure to radiation, not on the surrounding environment, because there is almost no surrounding environment to exchange heat with. This lack of atmosphere also means there is no scattering of light. On Earth, the sky appears blue because sunlight is scattered by air molecules. In space, the sky is black, even when the sun is shining, because there is nothing to scatter the light. That blackness is another aspect of the emptiness, a visual reminder that space is not filled with glowing air or haze. It is a near-perfect vacuum, illuminated only by distant stars and the occasional reflection from a nearby object. There is also a psychological dimension to this quiet vastness. Human beings are used to environments filled with sound, motion and activity. Even in the most remote deserts or oceans, there is wind, water, or the rustle of life. Space offers none of that. It is silent and still on a scale that can be difficult to imagine, and yet there is something calming about that stillness when you think about it gently. The solar system is not chaotic or crowded. It is spacious, orderly, and slow-moving, with worlds tracing their paths in silence, separated by distances that ensure they rarely disturb one another. That spaciousness is one of the reasons planetary systems can remain stable for billions of years. If the planets were much closer together, their gravitational interactions would be stronger and more disruptive. The wide gaps between orbits help maintain stability, allowing worlds to follow predictable paths over immense spans of time. Another way to appreciate the emptiness is to think about how small spacecraft appear in comparison. Voyager, now billions of kilometers from Earth, is moving through a region so vast that even if another spacecraft were nearby, they might never see each other. The distances are simply too large, the volumes of space too immense. Communication across these distances also highlights the scale. Signals take minutes or hours to travel between Earth and distant probes, and those signals spread out as they travel, becoming incredibly faint. Detecting them requires enormous antennas and precise calculations. All of this reinforces the same idea. Space is not just big, it is mostly empty. And that emptiness continues even beyond the planetary region, beyond the Kuiper Belt, beyond the Heliosphere, and into the distant reaches of the Oort Cloud. The solar system in its fullest sense is not a crowded collection of worlds, but a vast domain where matter is sparse and distances are immense. There is something quietly humbling about that realization. The planets, impressive as they are, occupy only a tiny fraction of the volume of the solar system. Most of it is silent space, stretching outward in every direction, gradually blending into the interstellar medium. Understanding that helps answer a deeper question about size. When we ask how big the solar system is, we're really asking how far the sun's influence extends across that quiet emptiness. And that leads naturally to the next question, one that is not as simple as it first appears. Where does the solar system actually end? And at what point do we begin to say that we are no longer in our own cosmic neighbourhood, but in the vast space between the stars? It feels like there should be a clear answer, a boundary you could draw on a diagram, a line marking the transition from our cosmic neighbourhood to the wider galaxy beyond. But the more closely astronomers study this question, the more they realise that the solar system does not have a single, obvious edge. Instead, it fades outward gradually, and what counts as the end depends on what you mean. One way to think about it is in terms of gravity. The sun's gravity reaches infinitely far in principle, weakening with distance but never truly disappearing. Every object in the solar system, from the closest asteroid to the farthest comet in the distant Oort Cloud, is held in orbit by that gravitational pull. Even objects thousands or tens of thousands of astronomical units away are still, in a sense, part of the sun's domain. If we define the solar system this way, then its outer boundary might lie at the farthest distance where objects remain gravitationally bound to the sun. That would place the edge somewhere in the outer Oort Cloud, perhaps 50,000 or even 100,000 astronomical units from the sun. At those distances, the gravitational pull of nearby stars and the tidal forces of the Milky Way begin to compete with the sun's influence. Objects can be nudged out of orbit, stripped away or perturbed onto long journeys inward. But gravity is only one way to define a boundary. Another way is to think about the environment of space itself. Inside the heliosphere, the solar wind dominates. Charged particles streaming outward from the sun fill the region, shaping the magnetic environment and helping shield the inner solar system from some cosmic radiation. Outside the heliosphere, the situation changes. The solar wind fades, and the particles surrounding you come primarily from interstellar space. This boundary, the heliopause, is often considered the place where interstellar space truly begins, at least in terms of the local environment. When Voyager 1 crossed the heliopause in 2012, it entered a region where the density and energy of cosmic rays increased, and the solar wind diminished sharply. It was the first time a human-made object had reached that frontier. and yet even beyond the heliopause, the Sun's gravity still holds sway. The spacecraft are still orbiting the galaxy along with the Sun, still moving within the broader gravitational domain of our star, so in that sense they have not completely left the solar system, depending on how you define it. This ambiguity reveals something important. The solar system is not like a country with a clearly marked border. It is more like a fading glow, gradually diminishing until it becomes indistinguishable from the background of the galaxy. If you were travelling outward, you would not encounter a sudden change, no sharp line where one region ends and another begins. Instead, you would notice subtle shifts. The solar wind would weaken, cosmic rays would become more common. The Sun would grow fainter in the sky, eventually appearing as just another bright star among many. At some point, the Sun would no longer dominate your surroundings. It would still be visible, still brighter than most stars, but it would no longer feel like the centre of everything. That psychological shift might be the most meaningful boundary of all. There is also another way astronomers think about the edge of the solar system, involving something called the Heliosphère. This is the region around the Sun within which its gravity dominates over the gravitational pull of the galaxy. The Sun's Heliosphère is enormous, extending perhaps a couple of light years in radius. Within this region, objects are more strongly influenced by the Sun than by any other star. Interestingly, the nearest star system, Alpha Centauri, lies just over 4 light-years away, which means that the Sun's gravitational sphere of influence extends a significant fraction of the distance to the nearest stars. This perspective changes how we think about the solar system's size. Instead of ending at the planets, or even at the Heliosphere, it may extend deep into what we normally think of as interstellar space, blending gradually into the gravitational fields of neighbouring stars. Another subtle boundary involves comets. Long-period comets arriving from the Oort Cloud are influenced not only by the Sun, but also by passing stars and the tidal forces of the Milky Way. Their orbits can be altered by events occurring light-years away. This means that the outermost parts of the solar system are not isolated, but are part of a dynamic interaction with the galaxy. The solar system, in that sense, is not a closed system. It exchanges material and energy with its surroundings. Comets can be ejected into interstellar space. Interstellar objects like the mysterious visitor, Oumuamua, can pass through the solar system, briefly becoming part of it before continuing on their journeys. These visitors remind us that the boundary between star systems is not a wall, but a region of transition, where objects and influences overlap. There is also a temporal aspect to this boundary. Over billions of years, the Sun moves through the Milky Way, orbiting the galactic centre and passing near other stars. These encounters can reshape the outer Oort Cloud, stripping away some objects and capturing others. The solar system's outermost regions are constantly evolving, shaped by events occurring far beyond the planets. So when we ask where the solar system ends, we're really asking several different questions at once. Where does the Sun's gravity cease to dominate? Where does the solar wind give way to the interstellar medium? Where do objects remain bound to the Sun, and where do they drift free? Each of these boundaries lies at a different distance, and each fades gradually rather than appearing abruptly. There is something quietly comforting about that idea. The solar system is not sharply separated from the rest of the universe. It is part of a continuum connected to the galaxy, influenced by distant stars, embedded in the broader structure of the Milky Way. If you were drifting far beyond the heliopause, looking back, the Sun would be one star among many, though brighter than most. The planets would be invisible, lost in the glare of that distant point of light. The solar system, which from Earth feels vast and complex, would appear small and quiet from that distance. And yet that small, quiet system contains everything we know, everything we have ever experienced, every story and memory and moment of human history. That contrast between the vastness of space and the smallness of our home is one of the themes that runs through astronomy. It does not diminish our world. If anything, it makes it feel more precious, more remarkable, a tiny oasis of life in a universe of immense distances. Looking outward from the distant edge of our own solar system, it is natural to wonder how it compares to others. For a long time, that question was impossible to answer, because until the late 20th century, we did not know whether planets existed around other stars at all. Astronomers suspected they did, of course, but suspicion is different from evidence. The stars were too distant, the planets too faint, and the techniques needed to detect them had not yet been developed. Then, in the 1990s, something changed. The first confirmed discoveries of planets orbiting Sun-like stars began to appear. At first, there were only a few, and many of them were surprising. Some were enormous gas giants orbiting extremely close to their stars, much closer than Mercury is to the Sun. These so-called hot Jupiters challenged existing theories of planetary formation and forced astronomers to rethink how planetary systems might evolve. Since then, the number of known exoplanets has grown into the thousands. Space telescopes and ground-based observatories have revealed an astonishing variety of planetary systems, some familiar in structure, others completely unlike our own. And that brings us to an interesting question. When we ask how big the solar system really is, part of what we are really asking is whether our system is typical or unusual. Is it large compared to others? Is it small? Or does it fall somewhere in between? To begin answering that, it helps to think about what we mean by size in this context. There are several ways to measure the size of a planetary system. One is by looking at the distances of the planets from their star. Another is by considering the outermost regions of cometary clouds and debris disks. Yet another is by looking at the gravitational influence of the star, the region where it dominates over the pull of nearby stars. In our solar system, the planets extend out to Neptune at about 30 astronomical units. The Kuiper Belt reaches perhaps 50 astronomical units. The Heliosphere extends beyond 100 astronomical units, and the Oort Cloud may stretch tens of thousands of astronomical units into space. That last number is particularly important. If the Oort Cloud exists as astronomers believe, then our solar system's gravitational domain extends a significant fraction of the distance to the nearest stars. But measuring the size of other planetary systems is much more difficult. Most exoplanets are detected indirectly, by observing the tiny wobble of a star caused by an orbiting planet, or by measuring the slight dimming that occurs when a planet passes in front of its star. These methods are most sensitive to planets that are close to their stars, which means that many distant planets remain undetected. As a result, our picture of other planetary systems is still incomplete. We may be seeing only their inner regions, not their full extent. Even so, some patterns have emerged. Many planetary systems appear to be more compact than our own. In some cases, multiple planets orbit within distances smaller than Mercury's orbit around the Sun. These systems can have several planets packed into a region that, in our solar system, contains only one. This might seem crowded, but it is simply a different arrangement. The planets in these systems are often smaller than Jupiter, and their orbits remain stable despite their proximity. There are also systems with giant planets orbiting far from their stars, and some with debris disks extending hundreds of astronomical units outward, suggesting the presence of distant reservoirs of material somewhat like our Kuiper Belt or Oort Cloud. One of the most interesting discoveries is that planetary systems often form in ways that differ from the neat, orderly picture we once imagined. Planets can migrate inward or outward over time, interacting gravitationally with one another and with the disk of gas and dust from which they formed. These migrations can lead to orbits that are highly elliptical or tilted, very different from the nearly circular, relatively flat orbits of the planets in our solar system. In that sense, our solar system appears to be somewhat orderly compared to many others. The planets follow nearly circular paths in roughly the same plane, and there are no giant planets extremely close to the Sun. That arrangement may have played a role in the long-term stability of Earth's climate and the development of life. But in terms of size alone, it is not yet clear whether our solar system is unusually large or simply typical. Some observed debris disks around other stars extend hundreds of astronomical units, suggesting that large outer regions may be common. On the other hand, many systems detected so far appear more compact, though that may be partly due to observational bias. Another way to think about this is to consider the distances between stars themselves. The nearest star system, Alpha Centauri, lies about 4.37 light-years away, which is roughly 275,000 astronomical units. If the outer edge of the Oort Cloud lies at around 100,000 astronomical units, then our solar system extends a significant fraction of the way toward the nearest star. That comparison highlights just how large our solar system really is, not just in planetary terms but in its full gravitational reach. It also reveals something else. The space between stars is not completely empty of structure. Each star may be surrounded by its own cloud of distant icy bodies, its own heliosphere or astrosphere, its own extended region of influence. These regions may overlap or interact over long timescales, creating a complex and dynamic environment on a galactic scale. So when we compare our solar system to others, we are really comparing regions that are often difficult to observe directly. We see the inner parts of other systems more clearly than their outer reaches, just as an observer from another star might see the inner planets of our solar system more easily than the distant Oort Cloud. There is also a philosophical aspect to this comparison. For centuries, people wondered whether our solar system was unique, whether the arrangement of planets and the presence of Earth were rare or common. The discovery of exoplanets has shown that planets are abundant. There may be billions of them in our galaxy alone. Some of these planets orbit within habitable zones, where temperatures might allow liquid water to exist. Others are gas giants, ice giants, or rocky worlds unlike any in our solar system. This diversity suggests that planetary systems come in many forms. Our solar system is one example among many, neither the largest nor the smallest, neither the most crowded nor the most sparse, but one variation in a vast range of possibilities. There is something quietly comforting about that realization. It reminds us that the processes that formed our world are part of a larger pattern, a pattern repeated across the galaxy, shaped by the same physical laws, the same interplay of gravity, motion, and time. And yet, even as we recognize that our solar system is one among many, it remains our home, the only planetary system we can explore in detail, the only one where we have sent spacecraft to multiple worlds and begun to map the distant frontiers. Thinking about other systems also helps put our own into perspective. The distances that feel enormous within the solar system are small compared to the distances between stars. Light takes hours to cross the planetary region, but years to travel from one star to another. In that sense, the solar system is both vast and small at the same time. Vast compared to our everyday experience, small compared to the galaxy. That dual perspective is part of what makes astronomy so fascinating. It constantly shifts our sense of scale, reminding us that size and distance are always relative to what we're comparing them with. By the time you've followed this journey from Earth outward, through the Moon's orbit, past the planets, across the Kuiper Belt, and into the distant regions where the Sun's influence fades, the idea of size begins to feel different than it did at the beginning. At first, the solar system may have seemed like a collection of worlds arranged in a tidy sequence. Now it begins to feel more like a vast landscape, a region of space so large that even light, moving faster than anything else in nature, needs hours to cross the planetary realm and years to reach its outermost gravitational boundaries. And yet, for all that vastness, this immense region is also home. Every human being who has ever lived has spent their entire life within a tiny fraction of this enormous system, on a small world orbiting an ordinary star. All of our history, all of our languages, every city and field and ocean, every memory and discovery has unfolded within a narrow band of space less than 1 astronomical unit from the Sun. That contrast can feel surprising at first. The solar system is unimaginably large, and yet our lives unfold within a space so small that, on a cosmic scale, it would be almost invisible. But there is another way to think about it, one that feels quieter and perhaps more reassuring. The fact that our lives unfold in a small region does not make them insignificant. It simply means that we are part of something larger, something that extends far beyond what we can see with our eyes alone. Consider for a moment how recently we began to understand the true scale of our surroundings. Only a few centuries ago, most people believed that the Earth was the centre of the universe, and that the stars were fixed lights embedded in a nearby sphere. The distances to the planets were unknown. The idea of other solar systems, other galaxies, or interstellar space lay far beyond imagination. Step by step, observation by observation, that picture changed. Telescopes revealed moons orbiting Jupiter, showing that not everything revolved around Earth. Measurements of planetary motion revealed the scale of the solar system. Spectroscopy revealed the composition of stars. Spacecraft carried instruments beyond the atmosphere, then beyond the moon, then beyond the planets. Each of these steps expanded our understanding, not by leaps, but gradually, patiently, one careful measurement at a time. There is something deeply human in that process. Curiosity leads to observation. Observation leads to understanding, and understanding leads to a new sense of perspective. That perspective does not diminish our world. Instead, it places it within a broader context, showing how remarkable it is that a small planet, orbiting at just the right distance from its star, could become a place where life emerged, evolved, and eventually began to ask questions about the universe itself. It is easy to overlook how extraordinary that is. When you think about the vastness of the solar system, it becomes clear that most of it is empty, cold, and silent. The planets are separated by enormous distances. The outer regions are dark and quiet, illuminated only faintly by a distant sun. The conditions that allow liquid water, breathable air, and comfortable temperatures exist in only a narrow region. And within that narrow region, on a small world with a thin atmosphere and a stable climate, life found a way to take hold. Over billions of years, simple organisms evolved into more complex forms. Forests spread across continents, oceans filled with living creatures. Eventually, a species appeared that could look up at the night sky and begin to wonder what lay beyond. That capacity for wonder is one of the most remarkable aspects of being human. It allows us to imagine distances far beyond our everyday experience, to measure the motions of distant worlds, and to understand the structure of a system that stretches tens of thousands of astronomical units into space. At the same time, it allows us to appreciate the smallness and fragility of our own world. Astronauts who have seen Earth from space often speak about the same realization. From orbit, the planet appears as a single, unified sphere, with no visible borders, no divisions, only clouds and oceans and land. The atmosphere, which feels vast from the ground, appears as a thin, delicate layer, barely visible against the darkness. That perspective, sometimes called the overview effect, can change how people think about their place in the world. It reminds us that the differences and conflicts that seem so important on the surface are small compared to the larger reality of our shared home. Thinking about the solar system can have a similar effect, but on a larger scale. It shows us that Earth is not the centre of everything, but one world among many, orbiting a star that is one among billions in a galaxy that is one among billions in the observable universe. And yet, even within that immense context, our lives still matter, because meaning is not measured in kilometres or astronomical units. It is measured in experiences, relationships, and the quiet moments of awareness that connect us to the world around us. There is also something calming about the steady, predictable motion of the solar system. The planets move along their orbits year after year, century after century, guided by gravity and inertia. The Earth turns day and night without fail. The moon circles the Earth. The seasons change in their familiar rhythm. These motions have been continuing for billions of years, long before humans appeared, and they will continue long after we are gone. There is a kind of quiet stability in that thought, a reminder that the universe operates on timescales far beyond our own. Sometimes, reflecting on those timescales can be surprisingly soothing. The worries and concerns of a single day, or even a single lifetime, are small compared to the slow, steady movements of planets and stars. That does not make them unimportant, but it places them in perspective. Another aspect of finding our place in the vastness is recognizing that exploration is an ongoing process. The solar system is not fully understood. There are still mysteries to solve, still regions to explore, still questions to answer. What lies in the distant Oort Cloud? How did the planets migrate in the early solar system? Are there undiscovered objects in the outer regions? Could there be life in the subsurface oceans of moons like Europa or Enceladus? These questions remain open, inviting future generations to continue the journey of discovery. And that journey does not require travelling billions of kilometres. It begins with curiosity, with the simple act of looking up at the sky and asking questions. Even tonight, wherever you are, the solar system surrounds you. The Earth is carrying you through space at tens of kilometres per second, orbiting the Sun, which in turn orbits the centre of the Milky Way. The stars you see are distant suns, each with its own history, perhaps with planets of their own. All of this is happening quietly, steadily, without any need for attention or acknowledgement. The universe does not rush. It unfolds at its own pace. There is something restful in that realization. The vastness of space is not something pressing or urgent. It does not demand anything from us. It simply exists, offering a sense of scale and perspective that can be both humbling and calming. When you think about the size of the solar system now, after tracing its structure from the inner planets to the distant cloud of comets, it may feel less like a number and more like a place. Not a place you could visit easily, but a place you belong to, a region of space shaped by the gravity of our star and the history of billions of years. And within that region, on a small world orbiting at just the right distance, you are here, listening, breathing, aware. That awareness, quiet and steady, is itself a kind of connection to the universe. Every atom in your body was formed in ancient stars long before the sun existed. The elements that make up the Earth, the oceans, the air, and all living things were forged in stellar interiors and scattered across space by supernova explosions. In a very real sense, we are part of the universe becoming aware of itself. That thought does not need to feel grand or overwhelming. It can simply be a gentle reminder that we're connected to something larger, something that extends far beyond our everyday concerns. As the night deepens and the sky turns slowly overhead, the solar system continues its quiet motion.